material here.
Yeah, it gets right into the heart of how electrons actually work inside atoms.
Specifically tackling that old puzzle, right? Why they seem so restricted.
Exactly. Why only certain energies, certain locations. It's all about, atomic stability and how atoms interact with light in such a precise way.
Because for ages, the picture was that simple planetary model, wasn't it?
Yeah.
Nucleus in the middle, electrons whizzing around like planets.
You made intuitive sense, yeah.
Yeah.
Easy to picture. But, like your sources clearly show, it fell apart.
The big problem being light. The spectra.
That was the killer. It couldn't explain why atoms only give off or absorb light at very specific, discrete colors, those spectral lines.
If electrons could orbit anywhere, like planets, they should have any energy, right?
Theoretically, yes, and interact with any color of light. But they just don't.
So then came the fix, the sort of quantum leap idea.
Right. Electrons could only be on specific energy rungs, and they'd instantaneously jump between them.
Absorbing or spitting out a photon with the exact energy difference.
Exactly. That explained the spectra, the distinct colors.
But as the sources point out, it left these huge questions hanging, didn't it?
Oh, definitely. Like, why only those specific energy levels? What makes them special?
And how on earth does an electron jump? I mean, does it just disappear from one place and reappear somewhere else without crossing the space in between?
Yeah, it feels like teleportation. A bit magical, maybe a bit unsatisfying if you want a deeper why.
Which is exactly what we're getting into today, using these sources, and especially that idea you flagged about cancellation.
Right. We're going to look at the fundamental physics behind it all. And the key is shifting from thinking of the electron purely as a particle.
Okay, so first step, ditch the tiny ball image.
Pretty much, yeah. Or at least, understand it's only part of the picture. Quantum mechanics, as presented here, describes the electron with a wave function, usually written as psi, that Greek letter.
And this wave function, it's not its location.
Not exactly. It describes a wave of probability. It tells you the likelihood of finding the electron at any given point around the nucleus.
A wave of probability. So its position isn't fixed, it's smeared out according to this wave.
Precisely. The electron's location is described by this probability distribution, this wave pattern.
And those orbital shapes we always see, S, P, D, F, how do they fit into this wave picture?
Okay, so those shapes, they're actually 3D maps showing where this probability wave can exist stably.
Stably, what does that mean here?
It means they show the regions where the electron's wave function forms a consistent, stable pattern. Specifically what we call a standing wave. The shape tells you where the probability of finding the electron is highest for that energy level.
Okay, electron as a probability wave trapped near the nucleus. Orbitals are the stable wave shapes. And this is where your idea, the cancellation concept from the sources, comes in.
Yes, this is crucial. The sources really emphasize that cancellation is the key to understanding why only certain energy levels, and therefore only certain orbital shapes, are allowed. It's the physical reason behind quantization.
And they use that guitar string analogy, which I found really helpful.
It's a great analogy. Think about it. A guitar string, fixed at both ends. You pluck it, it vibrates, but not just any old how.
Right, it plays specific notes, the fundamental, the harmonics.
Exactly. Only specific frequencies work.
Right.
Why? Because only at those frequencies does the wave travel down the string, reflect, and come back perfectly in sync with itself.
So it reinforces itself, creates a stable pattern.
Precisely. It sets up a standing wave, a pattern that looks like it's just vibrating in place. It's stable, self-reinforcing.
Okay, so what happens if you try to force a frequency that isn't one of those notes, one that doesn't fit?
It just dies out, right?
Yeah.
Or it sounds like a jumble.
Yeah, you don't get a clear tone.
And the reason is cancellation, or destructive interference. A wave at a disallowed frequency reflects back out of phase. The returning wave fights against the new waves being generated.
They cancel each other out.
Effectively, yes.
Yeah.
The energy can't build up into a stable pattern. The vibration destroys itself almost instantly. It can't be sustained.
Okay, got it. So now applying that back to the electron wave in the atom?
Right. The electron's wave isn't confined by physical ends like a string, but by the electric pull of the nucleus. It's trapped in that potential well.
Like a wave in a bowl, sort of?
Kinda, yeah. And just like the string, this electron wave can only exist stably at specific frequencies and shapes that fit within this confinement.
Frequencies and shapes where the wave interferes constructively with itself.
Exactly. Forming a stable 3D standing wave pattern. Those stable patterns are the allowed orbitals 1s, 2s, 2p, etc. Each has a specific shape and a specific energy.
So the orbital shapes aren't just random allowed zones, they are the shapes of these stable probability waves.
That's the key insight here. They are the configurations where the wave doesn't destroy itself. It fits the atom.
Okay, but then what about all the energies in between those allowed levels? Couldn't an electron wave technically have an energy value that's, say, halfway between ones and twos?
Well, you could imagine a wave function corresponding to that energy mathematically, but crucially, it wouldn't fit the atomic boundaries in a stable way.
Meaning,
Meaning, an electron wave trying to exist at that in-between energy would propagate, reflect off the edges of the potential well, and interfere destructively with itself.
it would cancel itself out, just like the wrong frequency on the guitar string.
Precisely.
So wait, does that mean the electron is there fleetingly, but we can't see it? Or it vanishes super fast?
This is a really important point the sources make. It's not just that it's hard to detect or exists for a tiny fraction of a second. A stable state for the electron at that energy is physically
Got it.
impossible. Yes. The wave function representing that energy configuration literally cancels itself down to zero everywhere within the atom due to destructive interference.
Wow. So it's not that the state is invisible, it's that the state cannot exist because the wave self-annihilates.
Exactly. These aren't just forbidden levels. They are physically non-existent stable states. The wave nature plus the confinement forces this.
That completely changes the picture of the quantum jump then. It's not a particle sneaking through forbidden territory.
No, the sources frame it entirely differently. It's not physical travel. It's a transition between allowed stable states.
Or reconfiguration.
Yes, a rapid reconfiguration of the whole electron wave pattern. From one stable standing wave, like a 1s orbital, to another stable standing wave, like a 2p orbital.
And absorbing or emitting a photon provides the exact energy needed for that specific wave transformation.
That's right. The photon's energy matches the difference in energy between the initial stable wave pattern and the final stable wave pattern.
So the jump is more like a pattern morphing instantly when the right energy arrives.
That's a much better way to visualize it, yeah. The sources do mention that the actual transition involves a very brief, complex state, a superposition, a mix of the start and end wave patterns that resolves or collapses into the final stable state once the interaction, like photon absorption, is complete.
It's really striking how your insight about cancellation really nails the core physical principle described here.
It seems to, yeah. It provides that satisfying physical mechanism. It's not just quantum rules say so.
It shows why the rules are what they are, the discreteness, the chunkiness of quantum energy levels. It's a direct result of waves needing to form stable, non-self-canceling patterns within the atom's confines.
Exactly. It's an emergent property of the wave nature of matter under confinement.
Okay, so let's just recap the key takeaways from these sources.
All right. First, the electron's behavior isn't about a particle jumping, but a wave pattern transitioning between stable states.
Second, those energy levels or spaces between the allowed orbitals aren't just skipped over. They represent configurations where the electron's wave function would destructively interfere and cancel itself out. They are physically impossible stable states.
And third, this principle of cancellation, the requirement for stable standing waves, is fundamental. It's what forces quantization, why energy, momentum, etc., come in discrete packets at the atomic level rather than being continuous.
Seeing it through this lens of probability waves and standing patterns really clicks, doesn't it? It makes the why much clearer than just rules.
It moves from abstract postulates to consequences of fundamental wave physics. It shows the energy levels aren't just assumed. They're derived from the nature of the electron itself and its environment.
Which leaves us with a really interesting thought to chew on, maybe.
Oh.
Well, if this core principle, wave cancellation, the need for waves to fit stably, is so fundamental for electrons and atoms, how else might it be shaping reality?
That's a great question. Where else in the quantum world does this requirement for self-consistent, non-canceling wave patterns lead to surprising constraints or structures?
Yeah, how does this deep rule about stability and interference sculpt the very nature of things at the smallest scales? Something to ponder.